Yeah, so my name is James Cole. I'm a PhD student at the Open University in the United Kingdom. And for the last couple of years, I've been working on using microwave heating to extract water ice from lunar simulants. So as we've heard over the last couple of days and over the last few years, one of the key aspects of ISIU would be to create lunar-derived rocket propellant. There's a few reasons for that. So it would possibly create a sustainable cislunar economy through the use of resupplying satellites in cislunar space, moving crew and cargo up from the lunar surface, and even possibly in the future to create missions that go to further destinations. And one of the best sources on the lunar surface for this would be water, due to its uses in liquid hydrogen, liquid oxygen systems. And as we've also already heard, the lunar poles are thought to contain quite vast amount of water ice, especially in the South Pole. And these would be forming in PSRs, at least the ones that are less than 110 Kelvin, which is the vital point at which any water ice that's been delivered to these regions would be stable and would stay there. L-Cross is the only in situ result we've got, so it's about 5.6 weight% water ice, and but remote sensing indicates that it could be even as high as 30 weight% in certain regions of PSRs. My research is looking at, is microwave heating the best way to gather this ice in very inhospitable regions with no sunlight at very low temperatures? So I'm going to quickly go over microwave heating and why it's of interest in the first place. So as we know, most traditional techniques rely on conductive heating. So you have a hot region that the heat transfers through the medium towards the colder regions. This is a bit of an issue with lunar regolith due to the fact it's got very low thermal conductivity. So if you want to heat a large area, it takes quite a long time. Microwave heating, on the other hand, with the use of electromagnetic waves, polar molecules that are in the sample will rotate back and forth, and this creates kinetic energy and therefore heat, and can do so quite efficiently and can heat up the entire volume at once. The equation on the top it highlights the two sorts of key factors in all of this. You've got the capital E, which is the electric field, which essentially just means if you put more power into your microwave source, you'll heat up more area or heat up more quickly. And then you've also got your epsilon, which is your dielectric loss factor. It's a material property. It's reliant on frequency and temperature, and is quite different for each material. The important thing to say here is that lunar regolith actually has a very high dielectric loss factor, which means heating is efficient, and that's why it's been used for sintering and 3D printing experiments, is we can get to molten temperatures really quickly using microwave heating. The issue arises in that the dielectric loss factor for water ice is actually really low. Even though it's very high for liquid water, it's actually really low for water ice. So my research is looking into how does the addition of water ice to lunar simulants affect the overall heating profile and therefore the water extraction. So to the experiments themselves, I've prepared samples using what's known as the permafrost technique. You add water to a lunar simulant, you let it diffuse through, and then you cool it down, to 100 Kelvin. I used water contents between 3 and 12 or 15 weight%. Basically, I went up to the saturation point of the simulant I was using. And there's a few reasons for this. The main one is that these PSRs aren't going to be a consistent water content throughout them. So I wanted to check, how does the microwave heating get affected by different water contents? Is it better suited to certain regions of PSRs? And then I also used two different simulants. So I used LMS and LHS from icylunar. And there's two reasons for this. So firstly, Mare simulants always have higher titanium and iron contents. And for sintering experiments in the high temperature domain, this seems to suggest that the heating profile is more efficient, and Mare simulants always reach the molten point in a quicker fashion. So I wanted to check, does this exist at colder temperatures? And also there's, especially at the South Pole, we're not really sure what the composition of these sites is going to be. And so I went for the two sort of end member cases of Mare and Highland to check, again, what are the effects of simulant composition on the overall extraction. So as Mahesh has already said earlier, we do have a bespoke microwave system at the Open University, which allows us to heat up samples in a vacuum environment. So I used 250 watt microwaves. I was going for the lower end of what's possible with our system. The main reason for this is I wanted to use what could be possible with a modern day rover or lander platform. And then I heated them up for about 35 minutes initially, and about 90% of the water was extracted. That's the first result, is that we'd extracted water from these samples at a lower power than ever been done before. But then I reduced it to 25 minutes, as I wanted it to be in a point where we could compare the extraction throughout all the different sample types and different water contents. And yes, we did these experiments at 3 millibar, and through the use of spectral identification and some mass spectrometry, we were able to identify that, yes, it was the water vapor that was being produced. So the figure on the bottom right with the purple plasma is actually the water vapor being produced. And yeah, so that's that. I should say that extraction in this case is measured simply by comparing the mass before and after heating. So to the results. So on your right, you can see a graph of water content along your x-axis and the water extracted in grams on your y-axis. The first thing to note here is that it's a bit difficult to explain, but the difference is the Highland simulants and the Murray simulants seem to have different extraction profiles. This isn't quite true. So when you're using the microwave system, there's normally an average absorbed power that's going into these samples. And the Highland sample, we were able to get a higher average absorbed power. So when we were heating them for 25 minutes, the actual differences in input energy was significant. So what I did to show this was I did a 30-minute run. So I just did an input energy calculation. And what this showed was that if you can see this black data point, it lies perfectly on the Highland simulant line. So what I'm trying to show here is that the simulant composition doesn't really have that much effect on extraction, which is quite surprising given what happens when you're going at the higher temperatures. And so what it indicates is that a microwave payload on the lunar surface, especially in these PSRs, wouldn't need to be as careful with what the composition would be. And then if you go along the x-axis, what you can see is that as you add more water, unsurprisingly, you get more water out. However, the really surprising thing we found is that at near the saturation points of both simulants, the extraction actually drops. This really wasn't what we were expecting. And I'm going to talk about that in the next slide. But really overall, what we found is that the heating time and energy input is crucial to maximizing your water extraction. So yeah, so what our theory about what's happened here is that before the saturation point, when you're filling the pore space with the liquid water before you freeze it, there's still space. So when the water expands as it freezes, the grains stay in contact. And the important thing to remember here is that the simulant grains are what heating up, because they interact with the microwaves more strongly. And by having this contact, you get more efficient heat transfer, and therefore your water extraction continues. At the saturation point, however, the pore space is then filled. So when it expands, you get the grains pushing apart. That reduces the contact area. And possibly more importantly, you get these regions of free ice forming. The water ice really doesn't interact with the microwaves at all. And therefore, these regions of free ice can actually be maintained. And therefore, that's why you get this drop off in extraction. Overall, this suggests that microwave heating might be better suited to low to medium ice deposits on the lunar surface. Okay. Yeah, so just in summary, we found that microwave heating can be used to extract water from cryogenic samples. We've done it at a lower power threshold than that's been done before. We found that compositional changes are not that important at lower temperatures for microwave heating, and that at the saturation point, this leads to quite a significant drop in the extraction. So for these points where we think there might be 38% of water, this effect could be even more pronounced and might be more of an issue. So microwave heating overall might be better suited for low to medium ice deposits. And all of this work can be found in a paper in Acta Astronautica that was published a couple of months ago. So yeah, that's me.